Welcome to the course on plasma physics and applications. Today we will study the basics of thermonuclear fusion. We look at the case of fusion energy in general, at the fusion reactions and the relevant cross-sections, at the schematic of a fusion power plant as I imagine it today, at the fusion fuels and their availability, and of course at the advantages that fusion can have. I would like to discuss the case for fusion energy by considering a single parameter that measures the development of a nation, called the Human Development Index. This combines three parameters: health, education, and richness, evaluated per individual, so per capita, in terms of the life expectancy, the number of years at school, and the gross national product per capita. In this plot, the Human Development Index is represented as a function of the electricity used per capita again. And what we notice is a very striking correlation between the two. In other words, in order to develop more, according to this very simplistic yet very interesting measure, countries need to use more electricity, or better, need to allow their individuals to use more electricity per capita. We also notice that at some point, corresponding roughly to this vertical dotted line, there is no need for an increase, for a further increase in the electricity used per capita to develop. This point corresponds roughly to the average of the Western countries. So what we want to have is an energy source that be available to all countries, and in particular to those that are on the left-hand side of this graph and therefore need to move on and move up in their development index. We want an energy source that has no negative impact on the environment and on the climate. That is, we want an energy source that doesn't produce a significant emission of greenhouse gases such as CO2. Global warming is now accepted as a scientific fact. We have images here that show examples of its consequences. We have the melting of glaciers. We have an increased frequency of extreme events such as droughts, floods, or heavy storms. Naturally, we want a source of energy that is safe, that doesn't create any significant risks for the population. We don't want situations like that represented in the picture, which is of course that of the Fukushima accident, to happen anymore. As I said before, the sources of energy that we look for must be available equally for all countries, and in particular for the countries that still need to develop. We want to avoid a situation in which, as we have today, 1.5 billion of people do not have access to electricity. A situation in which, if you represent a world map in a way that the size of the country is made proportional to the per capita energy usage, or is deformed according to that quantity, well, many countries cannot even be recognized anymore, as you can see here. Even continents cannot be recognized, almost cannot be recognized, such as Africa here. So to summarize this first part, we are looking for an energy source that is abundant, geographically distributed, that does not produce greenhouse gases, that does not create major risks for the population, simply that is compatible with sustainable development. My point is that such source does not exist today, and what we'll see in the rest of the lecture is that fusion can become part of the solution to this energy problem. So let us see how fusion works and its analogies and differences with respect to fission. To start the discussion, I plot here the binding energy per nucleon as a function of the atomic number. The curve here has a certain shape, which shows a minimum in the center of the plot corresponding to iron. The nuclear reactions can make us move along the curve, one way or the other. First way we have to move is to go down from the right. I say go down because as you go from large atomic numbers to smaller atomic numbers on the right side of the graph, the energy per nucleon is lower and lower. So if you have a reaction that takes you on that path, that means you can release some energy. And the energy that you can release corresponds to the difference in the vertical axis. So of course that's the way fission works, as represented here on the bottom. Fission works by breaking a very large nucleus, such as that of uranium, bombarding it by neutrons, for example, and creating smaller nuclei and energy. Fusion does exactly the opposite. That is, it combines light nuclei to form slightly heavier nuclei, and therefore goes down in the curve from left to right at the left-hand side of the graph. And you notice not only that you gain energy by, of course, going down in this curve, but also you gain a lot of energy in the sense that the slope of that curve is very sharp. The example shown at the bottom is that of deuterium and tritium, two isotopes of hydrogen, which, if combined, can give rise to helium and a neutron and a lot of energy. Once more, I say a lot of energy because the steepness of the curve is very large. In fact, fusion is the source of energy of the stars, so we know it works in nature. The stars work on the principle of putting together essentially 4 protons to form a helium-4 nucleus and, again, energy. The energy production comes from the fact that the mass of the products of the reactions is slightly lower than that of the fuels that enter into the reaction. So that creates a mass defect, which, according to the equation E=mc², coming from the Einstein relativity, of course, corresponds to energy. And to give an idea of what happens in the sun, every minute, a mass that is equivalent to the Matterhorn mountain is converted into energy. Let us look at the fusion reactions that we can have working on Earth in a reactor to produce energy for us. I have taken 3 examples here. Deuterium and tritium that fuse to produce a helium-4 and a neutron, which we have seen already. Deuterium and helium-3 that fuse to produce helium-4 and a proton, or deuterium and deuterium that fuse to produce 2 possible outcomes, a helium-3 and a neutron, or a triton and a proton. What we're seeing in the movie here is the thermal motion of the particles involved, and that underlies the difficulty of achieving fusion on Earth. The reason for that is that all these particles they were dealing with are nuclei, and therefore they're all positively charged. And because they have the same kind of charge, they repel each other due to the Coulomb repulsion. They repel each other in a way that they are kept sufficiently far for fusion reactions not to happen, except if the relative motion of these nuclei is strong enough, or the collisions are energetic enough, that they can come close enough and the nuclear force can take over. So when I say the motion is to be fast enough, or the collision strong enough, or energetic enough, I mean that the temperature has to be large enough. If the temperature is large enough, this random motion of the particles is very fast, and therefore collisions are energetic enough for the nuclei to approach each other at a distance where the nuclear force can take over and the fusion reactions can happen. Let's look at this phenomenon in a slightly more detailed way. We have said that the repulsion comes from the Coulomb potential, so we can calculate the height of the potential barrier that forms. We can see in this plot that is pretty high, almost 400 kV in terms of energy. So if we had to go all the way to the top of the barrier, we would need to have about 400 kV of energy in the relative motion of these nuclei when they are moving in a random fashion. However, we have an effect that helps us, and that is a quantum mechanical tunneling effect, which tells us that we actually don't need to go all the way to the top of the barrier, but we can tunnel through the barrier at much lower levels of energies. So that means we can achieve this passage through the barrier and then fall into the trap corresponding to the nuclear force, which will then lead to the fusion reaction, and therefore the energy that's released as a consequence of it, at energies or temperatures of the order of 10 to 20 kiloelectron volt, which is of course much easier to achieve than hundreds of kiloelectron volt. Let us look at the fusion reactions we have available on Earth to produce energy. We have seen that there are 3 possibilities: DT, D helium, and DD. We can quantify the probability for them to happen, or the difficulty to achieve them in a sense, by looking at their cross-section times the velocity average over the distribution function of the nuclei, which means their reactivity. And we notice immediately in this plot that the easiest of all to achieve, that is the one that has the largest cross-section, is the DT reaction. And that's why in the rest of this lecture, and in fact in the rest of the course, we will focus on this reaction only. One question naturally arises: why are we coupling plasma physics with fusion? Why is plasma physics an essential element of fusion energy research? Well, the answer comes exactly from the same plot we have just seen. Because if we look at that scale of temperatures, either in billions of kelvins or in kilo electron volt at the top, we notice that we are in a range of values that corresponds to a situation in which no ordinary matter can exist in the form of either solid or liquid or even gas. Only plasma can exist at these temperatures of the order of 10 to 100 keV or of the order of hundreds of millions of Kelvin. So plasma physics is an essential element of fusion energy research because at the temperatures required for fusion, only the plasma state of matter can exist. The second question I'd like to quickly address is, why do we speak of thermonuclear fusion? Why the term thermo? Well, the answer is in the plot I show here, which compares the cross-section for the Coulomb interactions, which means the interactions that are dictated by the electric force, and the cross-section for the fusion reactions in the case of dT here, as a function of energy. And we notice that for all the energies, there's a huge difference between the two. The Coulomb interactions have a much higher cross-section than the fusion collisions. So that means the Coulomb collisions are much more frequent than fusion reactions. So if we think of a monoenergetic beam, well, that would be scattered in a plasma before the particles can fuse. So in practice, that also means that we need to deal with a Maxwellian distribution, which results from an equilibrium generated by Coulomb collisions, a little bit like in a normal gas. And that's why we speak of thermonuclear fusion. So let's go back to our reaction that we have chosen for the first generation of reactors, at least, that is the DT reaction. Once more, there's the deuterium and tritium that collide energetically enough to fuse. Helium nucleus comes up of the reaction with 3.5 MeV of energy, and a neutron also comes out with 14.1 MeV of energy. So the fusion fuels are therefore deuterium and tritium. Deuterium is about 0.014% of the hydrogenic atoms everywhere, including in the oceans. That corresponds to about 1.6 grams per liter. So it's relatively easily available. Tritium, on the other hand, does not exist in nature because it's radioactive and short-lived. Its life is about 12.5 years. However, it can be produced from lithium in a process that we call breeding. And lithium, in turn, can be mined or found in the ocean water in the amount that's about 0.15 grams per cubic meter. How is tritium produced from lithium? There are two possible reactions. The neutrons that come out from the fusion reaction itself can react with the lithium that's present around the plasma, that we will actually install around the plasma, in two ways. There's a reaction with lithium-6 on the top, or a reaction with lithium-7 here at the bottom. We'll concentrate on the first of the two for the simple reason that despite the fact that the lithium-6 is only about 7% of natural lithium, the cross-section for this reaction, which implies that its probability, is much larger than the other one. And in fact, that's why in the picture represented here, we only show that possibility. So it's lithium-6 that will react with a neutron. And what will be the byproduct of this reaction? That will be exactly what we want. It will be a tritium. It will be also helium-4, and in fact, even some energy. So that's how we produce tritium in a plant. In practice, what we'll do, we will surround the plasma with a blanket, as we call it. It is a system that has essentially lithium in it, so that this nuclear reaction between the neutrons produced by the nuclear fusion reactions and lithium can occur. Of course, there are different concepts and technological details in different approaches. We see here a picture from CA in France. Different concepts for this blanket for breeding tritium, but all of them are based, again, on the presence of lithium. We're now ready to look at the schematic of a fusion reactor, at least as we imagine it today. So from the outside, what I call the primary fuels, we will have lithium that will come and deuterium that will be injected in the plant. Lithium will go and will stay in the blanket around our plasma. Deuterium will be injected directly in the plasma. In the core of the plant, of course, we have the plasma itself, which will be hot enough to produce fusion reactions. The neutrons that are issued by these fusion reactions will react with the lithium in the blanket and form tritium. This tritium will be purified and then injected again into the plant. So no tritium will come in, no tritium will come out of the plant. What will come in, again, will be deuterium and lithium. What will come out will be some helium, and most importantly, energy. Energy will be collected in the blanket by a fluid. They will exchange the heat, and that fluid will make a conventional turbine work via the usual cycle that we operate in different kinds of power plants. The result will be some electricity that will be injected in the grid. I'd like to discuss the advantages of fusion now. First of all, there's a fantastically high energy density. And to illustrate that, I prepared a table here with different kinds of fuels for different kinds of sources of energy we have available today. And I sort of rank them in terms of their specific energy. That's the energy content they have in terms of megajoule per kilogram, so energy per mass. I start with water. I consider a 100-meter high dam just as a reference. The number that water has as an energy content is very small, is 0.001 megajoule per kilogram. I move on to coal. Coal, of course, needs to be burned, so needs to give rise to CO2, greenhouse gas, and so on. Its specific energy is about 30 megajoule per kilogram. Oil, same issue of fossil fuels, 50 megajoule per kilogram. And then we have a huge jump because I'm moving to nuclear reactions. First example, instead of fission, I take here uranium-235. Instead of 30, 50, or tens of megajoule per kilogram, now we have a total game changer. We have 85 millions of megajoule per kilogram. And the next step, which is even much higher than fission itself, is fusion. For DT in this example, we have 350 millions of megajoules per kilogram. As close as you can get to just transforming directly all the mass into energy according to just the mc square equation, which corresponds to having 90 billions of megajoule per kilogram. So fusion is as close as we can get to that number. Fantastically high energy density. And to quantify this in a practical example, as shown in the picture here, I like to take 1 liter of seawater. That corresponds to 33 milligrams of deuterium. Then I take 5 grams of lithium ore, corresponding to 50 milligrams of tritium. The energy content in this combination corresponds to the energy content of almost 400 liters of petrol, which is more than 2 barrels. Because of this huge energy density and because of the amount of fuels that we have available on Earth, fusion is practically inexhaustible in terms of its fuels. The picture here shows a lithium mine in Nevada, so lithium can be mined on the Earth crust. But both lithium, in fact, and deuterium can be found in ocean water. Ocean water is everywhere, almost everywhere, and in large amounts. The two pictures of different oceans here remind us that ocean water is very well distributed geographically, for example, as opposed to fossil fuels. So not only are the fuels practically inexhaustible, but they are also extremely well distributed geographically. In terms of the environmental impact, first of all, there's no greenhouse gas emission from fusion. There are no waste products, because the byproducts of the reaction is simply helium. There is no long-lasting radioactive waste. Even the activation of the reactor itself is a relatively minor problem. This is illustrated in this plot, which shows the radioactivity level of the plant after shutdown as a function of the number of years after this shutdown for different cases. We see the red line here is that of a fission reactor, is a light water reactor in this case, which stays very high in this curve all the way to about 10,000 years after it's shut down. Situation of fusion is very different. Even with materials that we have available today, for example, the ferritic steel, this is the yellow curve here, we go down relatively fast in this radioactivity level. We reach the level of the coal ashes, so the level at which we really don't worry anymore about the radioactivity of the plant, after tens of years as opposed to tens of thousands of years. If we go for more advanced materials such as vanadium alloys or silicon carbide composites for fusion, that level is reached really after only very few years, or even reached from the very beginning in the case of silicon carbide composite. So we have seen that fusion has a huge energy density, that its fuels are practically inexhaustible. The fusion has no bad effect on the environment. What about its safety? Well, that's also a very, very important advantage of fusion. First of all, there is no link between fusion and nuclear proliferation. Second of all, the concept of fusion reaction is not based on a chain reaction, so there is no risk of loss of control of the reactions in the sense there is in a fission reactor. And last but not least, there's always a very, very small amount of fuel in the reactor at any given time. We're talking about grams of fuel present in even in a gigawatt level reactor, as illustrated pictorially in the movie that you're watching on the slide. And even in the case of a major accident, the release of the fuel will be in such minute amount that there will be no risk for the population even just around the reactor site. In summary, we have seen that fusion works by putting together 4 hydrogen nuclei to create 1 helium and a lot of energy. Fusion actually works already in nature because it powers all the stars in the universe, including our sun. The fusion reactors on Earth will use the DT reactions. But even for the DT reactions, we need temperatures at which matter exists only in the plasma state. The primary fuels for fusion are deuterium and lithium, which are both abundant in the oceans and in the Earth's crust. So I believe fusion can provide a solution to the energy problem that's compatible with sustainable development.